So Ohanian 2.35 has a boy at the edge of a cliff, throws a rock upward at a 45-degree angle, comes back down to the height where he released it 2.25 seconds later, then continues falling and hits a lake 4 seconds after release. Not after it returns to that height, but after the release. How far below the boy is the lake? And how far horizontally does the rock move after he throws it? So we're doing homework 2, Ohanian 4.35. And the problem that's complicated, I like to start with a picture. So let's draw a figure. Okay, the boy throws a rock at an initial angle, so I'll call it theta naught, and that angle is 45 degrees. Okay, and somewhere down here there's a lake, and I am going to define my x and y coordinate system, x horizontal, y up, but with my origin at the point where the rock is released, so the lake is at some negative y below that. Okay, that's arbitrary. You could have put your origin down here if you preferred, or other places. So let's see how we can approach this. We're given it takes a time t equals 2.25 seconds in order for the rock to return to its initial height, y equals y naught, okay, which in my case is going to be 0, but okay. And that means we can solve, because we know the acceleration is a constant negative g down. Gravity is the only thing acting on the rock. So given this information, I can solve for v naught in the y direction. I'm not even going to worry about the x direction yet. The y direction, the time usually comes first in a problem like this. And I have enough information to do something useful in the y direction because I know it's 2.25 seconds to go up and come back down again. So I can use the expression y equals y naught plus v naught in the y direction, the y component of the original velocity, t, plus 1/2 ayt squared. That'll be enough for me to solve for the initial velocity in the y direction because I know the change in height, it's 0. And I know the acceleration, and I'm given the time. Okay, so I can use this to say that v naught in the y direction is just 1/2 gt. These two cancel each other out. This squared cancels that t. So v naught y equals 1/2 g times t. Ay is g. Okay. Remember, there's a negative sign here, but I'm taking it to the opposite side of the equation. So now I can just plug in the numbers. 1/2, 9.81 meters per second squared, 2.25 seconds, and voila, I know the original velocity in the y direction, the component in the y direction. Okay. Given that, I can go ahead and solve for where the lake is, because I'm told that it takes a total time of 4 seconds for the rock to hit the lake. And so you could do this a few different ways. The time to fall to the lake from the point where it comes back down to here, okay, it's 2.25 seconds to here, but the time from here down to the lake is just going to be 4.00 seconds minus 2.25 seconds. So it's falling below the original height for 1.75 seconds. And so this is just like a problem where you're told how long it takes to fall given the initial downward throw. And I can use my same expression again. Y equals y naught plus v naught yt. Now I'll just put in the acceleration is minus 1/2 gt squared. And y naught, remember, I picked to be 0. So this is just the position of the lake if I plug in the time, 1.75 seconds, and the 11 meters per second down. Or I could use it up and use the total time. Like I say, you could do it either way. So the position of the lake is going to be minus 11.0 meters per second, because I'm using this time instead of the 4 seconds, but you can do it either way, times 1.75 seconds minus 1/2 9.81 meters per second squared times 1.75 seconds squared. pull out your trusty calculator, plug in the numbers, and you'll find negative 34.3 meters. That's the distance of the lake below the original position at which the stone was thrown. Now you're asked, well, how far does it travel horizontally? So we can use there the fact that the horizontal position at any given time equals x naught. But remember, I defined that as 0. That was my wise choice up here of the original coordinate system. Plus v naught xt, the x component of the original velocity, plus 1/2 the acceleration in the x direction t squared. But there's no acceleration in the x direction. So I have a pretty simple expression. Now we have a 45-degree launch for theta naught. And so that tells me that v naught x is the same as v naught y. They're both 11.0 meters per second. If that wasn't the case, you would just have a little bit of trig to do. Okay? If you knew this angle and you knew this velocity v, if you knew this y component, then knowing this angle, you could work out what the hypotenuse is, and then you could work out the horizontal component. But they made it easy in this case by saying 45 degrees. So the two x and y components are equal to each other. So I can just quickly write out that x equals v naught x, also 11.0 meters per second, times the total time now, because it's traveling in the x direction for the total 4 seconds, or 44.0 meters. Done. Now the answer in the back of the text is actually wrong in this case. He mistakenly, or whoever wrote those solutions, mistakenly used 4.0 seconds plus 2.25. They didn't read the problem carefully, and that would lead to 68.8 meters. But not what the problem says. So we're done.